Good, looks like we're good to go. Okay. Hi, everyone. Hi, YouTube. Let's slowly get started. We'll continue a little bit with LPs today, where we started yesterday. There's one more comment on integer linear programming that we need to make. And then we'll finally use LPs for something. And also probably get to some lower bounds. We discussed last time what LPs are and how you can use them to model problems. There was max flow, and we've seen some other examples, and we've seen normal forms in linear algebra notation. There they are. And then the simplex algorithm as a rough idea, at least. One thing that occurred to me only after someone asked a question after the lecture yesterday, you can actually stick with this geometric intuition and pretend that's the actual LP you start with. And then for the linear algebra version here, you basically just interpret the LP to have these slack variables that we introduce. And then the basic solutions that we defined here essentially correspond to picking the slack variables of some vertex and setting them to 0. So it's the non-basic variables that you should imagine picking. So in our example, the actual LP we started with had dimension 2. It's in the plane, but it had I think it was 12 constraints. So if you turn these all into equality constraints, you end up with 2 plus 12 variables in total, 14. And a vertex previously corresponded to picking 2 constraints and then taking the intersection of those 2 constraints. So assuming that these 2 constraints are satisfied with equality, that's what gave you any of these points, right? All of these points, whether or not they were feasible, are the intersection of 2 constraints in 2D. And that corresponds in the algebraic version to pick, well, all but those 2 as a basis, because the basis is the number of constraints in the new problem, which is still 12, but we have 14 variables. So a basis is 12 of the variables. The non-basic variables are the 2 leftover variables. And you could interpret these as just the slack variables for those 2 constraints. And then the non-basic variables are set to 0, which means exactly you're forcing your solution to be tight on those 2 constraints. So there's a more direct correspondence between the two views than I presented yesterday. The only catch with what I just said is, what if your non-basic variables are the 2 original ones, or one of the 2 original ones, and not the base variables, or not the slack variables? Then you need the reformulation, and it's algebraically nothing different, but the intuition kind of dies at this point. I still thought this is maybe a useful thing. For next iteration, maybe I have to rewrite this bit. Okay, so we've seen simplex algorithm and some other methods. And that brought essentially the LP part to an end for this part. We'll revisit LPs and the whole theory of duality again at a later point, which is where things get really interesting for algorithmic uses. But for now, that's all we need to know for LPs. And that's where we continue with the integer version of it. In the previous sections, we've seen linear programs, how to model problems with them and how to solve them. And there's one piece missing for many kinds of problems that we would want to model. And that's what we'll cover in this section. And to motivate that, remember so that many natural optimization problems actually fit the setup of LPs. They have a linear objective function and linear constraints. For example, the knapsack problem that we've seen in the pseudo-polynomial chapter in more detail, as the optimization problem. So there's items 1 up to n. They have some weights and they have values. I've written them here in vector notation because we're used to that anyways from LPs. And then we have a weight constraint for the knapsack. And the goal is to select a subset of the items with maximal value, but weight at most the constraint, the capacity. So you can easily write this as a linear program where you maximize the dot product of values and the variables, where the variables are such that you set the variable to 1 if the item is included, and you imagine it's 0 if not. So the variables should be between 0 and 1, and we want the knapsack constraint to be satisfied. So each item, the dot product with the weights is the total weight. You sum up the weighted, the weight contributed by each item in the set, and that should be at most b. So far so good, but of course if you've seen this before, then it's clear. So we could use an LP solver to get an optimal solution, an optimal x for this LP. But there must be some problem here because the LP solvers are polynomial time algorithms. The knapsack problem is NP complete. So this looks like a contradiction here. And of course, what's wrong is that the solution we get back from the LP solver might not make sense in the combinatorial problem. Specifically, it might not be an integral solution. When we set up this LP, or when I set it up for you, what we really had in mind is that these xi should be either 0 or 1. You can either include the item or not. But the LP doesn't have that notion. It's a variable between 0 and 1, but it can be any real number. And in particular, it can get really nonsensical if, for example, you have just a single item that you can choose from, but that item itself is already too heavy to take. Then the actual solution must be 0. You cannot take anything. But for example, if the weight is twice the capacity, the non-integral optimal solution that the LP will spit out is just taking half of that item. That still fits your constraint, and it gives you half of its value. So in general, the solution for an LP doesn't help at all in solving the original optimization problem. In general means for some problems it doesn't help at all. And the knapsack problem is one where the difference here can be big. So what can we do? Well, one thing is we can brush up the language of our optimization problems. So we can add the option to add integrality constraints. So the general form we've seen in the exercises, the 0-1 version, where you constrain the variables to be either 0 or 1. But you can also have the more general version where you just restrict them to be integers. And that's what we call an integer linear program. It's as before, an LP, but now the ILP adds this integrality constraint. In full generality, you can have a mixed integer linear program where some variables are continuous and some are discrete. So you would only have some of the variables restricted to c to the n. But here we'll focus on the case that all variables are integral. That's the one that's most relevant for us. It just is worth noting that the solvers that exist for solving these problems in practice can usually deal fine with mixed integer linear programs. If we go back to our knapsack problem, it's easy to turn the knapsack LP into such a normal form ILP. You just add the constraint of integrality, and now we're modeling exactly the problem we had. If all the variables are supposed to be between 0 and 1 and integral, then they must be either 0 or 1. And then this encodes exactly the original combinatorial problem. Something we haven't talked about at length before is the kind of general geometry of linear programs. I wanted to at least drop this vocabulary here. A polyhedron, polyeder, the German word, is the feasibility region of an LP. And this is essentially a convex polygon in higher dimensions. So formally, it's just the intersection of half spaces in some n-dimensional space. And of course, for a specific LP given in our normal form, you can write this concisely as a set. It's a set of all vectors x so that they can satisfy the constraints. That's the feasibility region of a linear program. If you go to an integer linear program, you have to take that same region and take the intersection with the integers or the integer lattice in higher dimensions. And so it's just the same p, but intersected with z to the n. That's a discrete set now. And so we shouldn't expect the same kind of techniques to work. But we'll still make some use of this. At this point, maybe I should have put this on the slide as well, even though we've covered it before. Clearly, solving integer linear programs in general is NP hard. Basically, you've seen, or well, we didn't do the proof in the lecture, but the 0-1 integer programming problem was listed as one of Karp's original NP hard problems, NP complete problems. So even the restriction to just binary variables is hard. And that, of course, translates to the general problem. And you can also reduce easily many kind of problems to integer linear programming. There's one on the slide, right? We know the knapsack problem is NP hard. So if you could solve in general ILPs, you could solve this NP hard problem. Hence, ILP is also NP hard. So we shouldn't expect fast algorithms in sharp contrast to linear programs. Also, what I said earlier about the practical solvers for integer linear programs, mixed integer linear programs, they do work, but not for such big problems. You can do some clever branch and bound algorithms for integer linear programs, but I guess a few dozen to a few hundred variables might still be doable if you're lucky. But that's much, much different to the millions of variables you can easily solve even with not super sophisticated LP solvers. What else? What can we still do despite the fact that the problem doesn't allow general efficient solutions? One thing we can do is we can, from this obvious relation on the feasibility regions, if we're minimizing, then we'll get that the optimal objective value that the LP spits out can never be worse than what the integer linear program gives you, just because all points that are feasible for the integer linear program are also feasible in the linear program. You're just dropping one constraint. And so this is something we can use to our benefit, because again, remember, LPs can be solved quickly. In theory terms, polynomial time is for free. So we can take a combinatorial, one of the many combinatorial optimization problems that you can represent as an ILP. And we can define its LP relaxation, which is just take this ILP and strike out the integrality constraint. Then you get the LP relaxation of this ILP. I guess I should be a bit specific that you can oftentimes model the same combinatorial optimization problem in slightly different ways. You can encode it in different ways as an integer linear program. And so there might be different ways to get an LP relaxation. And the specific LP relaxation is always specific to one way to model the problem. And there can be more or less smart ways. But for now, let's ignore that. So The idea is that it's a cheap way to get some lower bounds for the problem if it's a minimization problem. And this is indeed something we'll come back to. Let's do a small example to see this in action. Here's the independent set problem. One of the other many problems you can write as an interlinear program. Again, to remind you, it's a graph that we're given, and we try to find an independent set. So a set of vertices, subset of vertices that have no edges in between, and we'd like to find the largest such set. Then we could model this as an interlinear program by giving each vertex a variable that's either 0 or 1. Is it included in our independent set or not? And then we can simply write this out almost flows directly from the natural language formulation. We maximize the number of vertices that we can pick. They're between 0 and 1, the variables. There are 0 or 1. And then the constraints are for every edge, we can include only one of its endpoints at most. And that we can write as the sum of the endpoint variables has to be at most 1. Now, because they're either 0 and 1, this is essentially a way to express the Boolean or. We can include one or the other, but not both. So I guess it's with the less or equal 1, it's a NAND. And the linear program relaxation on the right just replaces the binary constraint with upper and lower bounds. So the variables are still bounded between 0 and 1, but they need not be integral. Okay. At this point, I want to introduce another name. We'll come back to this in other places too. That's the notion of an integrality gap. And technically, it's just the optimal value that you get for the ILP divided by the optimal value for the LP. And the question is, how far away can these be from each other? So this is defined for a specific LP relaxation, because you need to be able to talk about one ILP and its LP. But you can also to a whole problem, integrality gap of a problem, in which case people usually mean the best way to get an ILP for that problem and an LP relaxation for that ILP. This is a bit less well defined, but you sometimes find this language in the literature. We've seen some example early on where this was actually not a big gap. Our apple farmer had this solution where he was told to build a fractional number of trees of this one variety, which is not really possible. So if you round this down and just give up that third of a tree, the revenue goes down from 155,500 to 155,450. So you lose some 80 euros, but if you take the ratio, it's actually a minuscule difference. So if the integrality gap is small, we can potentially use this, take the ILP for the problem, avoid the integrality constraints, solve it as if it was a continuous problem, and try to make sense of that solution, as we did here, essentially by rounding. And we can hope to get approximate solutions from that. And that's indeed something we'll revisit in a more structural way when we talk about approximation algorithms. Unfortunately, in general, the integrality gap can be really, really bad. And here's kind of a cartoon of what this can look like. Suppose you have a small LP with these three constraints in 2D. So the purple region again is the feasibility region. if you take the integer version of that, then only these two blue points are really contained inside the region. You have to zoom in a bit. Also, the exact numbers don't matter that much, but you see how if the objective function improves in this direction, you can shift it all the way to this thin, acute point here of the triangle to get a really good solution for the LP relaxation, but you're stuck at this integer point far on the left because there's just no other integer point contained in this. So that's kind of a sketch why the integrality gap can in general be really big, and that's even for two-dimensional problems. To convince you that this is a real problem, let's look at the independent set problem again. We've just seen the formalization right here, the ILP and the linear program relaxation. So we had a constraint for each of the edges, and the variables are just between 0 and 1. Now the bad case occurs if you think about a huge complete graph. In a complete graph, the only independent sets we have are isolated vertices, single vertices, because whenever you pick two vertices, they have an edge. But what happens in the linear program is we can still satisfy all those constraints by setting every vertex to 1/2. So we pick every vertex half into the independent set in this fractional version. We satisfy all the constraints, but the solution is completely meaningless. And what's worse, its optimal objective value is n times 1/2, which is far away from this value of 1 that you get in the integer program. So you can think of this as the high-dimensional version of this picture on the left, where things get completely out of control. You have no bound on the integrality gap in the worst case in general problems. So it's not a magic silver bullet that somehow solves things automatically. But I'll point to that unit 12, where we'll see for some problems this is indeed helpful. So before we go back to our fixed parameter problems, I substantially reshuffled this part, so there we are. So the example we'll see is somewhat specific, but I guess you can think of it as in a way, using an LP relaxation as a cheap pre-processing tool. So maybe that isn't so far-fetched an idea. In this section, we'll look at how to use linear programming relaxations to get kernelizations for problems that we've seen before, and indeed better kernels or smaller kernels than what we've achieved with our more ad hoc reduction rules before. And we'll revisit our good old friend vertex cover. Remember, it's one of those really well-studied FPT problems. It is in FPT. You can easily get a 2 to the k search space algorithm. We could actually get down to something 1.3 to the k. That's not a result I've shown you in detail, but we could get, I forget what it was, 1.4 something. Was that the 1.6 to the k? Well, this was the best result that I only cited in the previous unit. So we know this is from the perspective of fixed parameter tractability, is a relatively tame problem. But let's look at it again from the kernelization perspective. The best thing we had was a quadratic kernel. So given an arbitrary graph and this parameter k, what is your threshold for the size of a vertex cover? We could use this high degree rule, so just from removing every vertex of degree greater k, we could get the graph shrunk to something of size k squared at most. So we'll see something slightly better here now. First of all, let's rewrite it as an integer linear program. For vertex cover, that's also very easy. We have a variable as before for each vertex. Is it part of our vertex cover or not? Here we try to minimize the number of vertices that we have to pick, but then the constraint is for every edge, we have to pick one of the two vertices. I guess the formulation as integer linear program, again, makes even more explicit why vertex cover and independent set are so closely related. You almost see it immediately that they're kind of opposites of each other. Right? Remember, independent set was the same structure. It said maximize the number of vertices you pick, and the constraint was okay, let's use UV here, was at most 1, except as opposed to greater or equal 1. So they're really kind of doing opposite things. Okay, but that's beside the point, just because we talked about independent sets a moment ago. So forget about this, focus on the integer linear program for vertex cover. Now again, that's a precise representation of the problem, but we cannot solve integer linear programs faster than the original problem. So instead of this, we consider the relaxation. So we just get rid of the integrality constraint, or more precisely, we replace it with inequalities. And we don't need the upper bound of 1 here. It's enough to constrain the variables to be non-negative, just because the minimization already makes sure that using anything more than 1 is never going to be an optimal solution. So that's another kind of trick here. It's a general approach that you'll see in many places, and it sometimes makes things magically more approachable, the resulting linear programs. So we essentially grow the feasibility region. But in a way that we don't get any new optimal solutions. Let me write the set of optimal solutions as well. Because sometimes this is relevant. Usually we want to grow the region in a way that we never make any new optimal solutions. So we take that linear program, minimize the sum of xv, subject to the sum of two endpoints of an edge being at least 1, and all variables non-negative. And throw that into your favorite LP solver. You'll get some solution back. You can prove that it will never have variables set to a value larger than 1. And they will all be between 0 and 1, and they will satisfy the constraints, but they might be fractional. And specifically, we'll get some. So let's write this down, even though I just said it. it will be between 0 and 1. Whatever this optimal solution will be, I have to change that. Imagine that's a bold X instead of X with an arrow. Whatever that solution will be, we can define 3 sets of vertices now, depending on what their value, their variable has as value. There might be some that have exactly value 1/2 in the optimal solution. And those are in this set B0. And the other 2 are either below 1/2 or above 1/2. Okay? Now the claim is we can take these 3 sets, again, maybe say, what's a good mnemonic for I and C? I don't remember what I thought about when these were named. Well, I is inferior, so it's less than 1/2, and C is somehow the ones above 1/2. The claim is you can, without loss of generality, always take the vertices in C0 as part of an optimal vertex cover. And you never need to take any of the vertices in I0. And then, of course, there's the ones in V0 left where we don't know. But we'll see that we can essentially restrict the input to just those vertices in V0. And that's going to be the hard part of the problem. In other words, the kernel of the problem. And you can bound the number of vertices that are in V0. And so if you take a step back, like what have we done? We take our vertex cover problem, we write it as an ILP and take the relaxation. So far, so standard. And now we get some optimal solution back, and we can just, from the optimal solution, learn a lot about potential optimal vertex covers, and in particular, how big an optimal vertex cover is. I still find that somewhat surprising that this is this kind of detour via LPs gives you so much direct information about this graph. So let's prove this and kind of demystify what happens here. So we'll first prove this claim 1. And then the second part is actually not that hard. So the thing is that the statement here, to be precise, it only says there is some minimal vertex cover that contains all of C0 and nothing of I0. There might be other optimal solutions. So when we start, we assume that S is some optimal vertex cover. The goal will be to show that we can modify S to satisfy, we call that one S star. We can modify S star to be like the S in the claim without making it bigger. Okay? So we define the modified solution where we take S star, we take out all the ones that are in I0, and then we add everything in Z0. And we claim that's as well an optimal vertex cover. And that claim has 2 parts, right? It needs to be a vertex cover and it needs to be optimal size. But let's rewrite this first. We can essentially rewrite this as this. So where now Si is all the elements that are really in S. So sorry, S star. Here I'm taking out an unknown number from I0, so I'm just giving that a name. All the elements in I0 that are in S star, these are the ones I want to not have in my solution to satisfy the claim. And conversely, this S bar C is everything in Z0 that's not in S star already. So part one is S is a vertex cover. Let's try to prove that first. When we add more vertices from this SC bar, we will not uncover any edges. So the only potential problem could be the vertices that we remove, right? These are certainly the only ones we have to worry about. So suppose we have such an edge. And say V is in I0. By definition, I0, these were the vertices where the corresponding optimal solution of the LP had a value less than 1/2, right? So XV star was less than 1/2. But the solution has to satisfy the constraints, so the other endpoint has to be strictly greater 1/2, which means this W is in Z0 by definition of that set, which means we'll eventually include W for sure. So we might remove V0 if it even was in the solution S star. But even if we remove it, we make sure that we add back in the other endpoint, so that edge will be covered. Okay? And that's basically all. Any other edges we don't touch. If it has no endpoint in V0, whatever endpoint it previously had in S star, it'll still be there. We don't remove it. So that proves that our constructed set S is indeed a vertex cover again. That's good. Then we continue here with the claim that the size of S is the same as the size of the optimal solution, which means it's also an optimal vertex cover. And the way we've rewritten our construction for S, so here, so the dot above this union here means disjoint union. It's just a way to express that I kind of know that the two sets will be disjoint. There's no notation for disjoint set difference, but if there was one, it probably will be a backslash with a dot above. I don't know, right? So what I'm saying here is this is also a disjoint set difference, which means, I mean, this is of course nonsense. A set difference for disjoint sets wouldn't do anything, but we're not. There's nothing in this set Si that is not in S star. It's kind of you're taking the set difference where the set you subtract is a subset. Okay. Let's doesn't hurt to write it down. That was the idea of the construction. I guess I said it maybe verbally, but Si is a subset of S star, whereas the SC bar is disjoint from S star. So to say something about the size of S, you can take the size of S star, you subtract the size of Si, and then you add the size of SC bar. So let's do one more step here. So the size of our S, stay here. The size of our S is the size of S star minus the size of Si plus the size of SC bar. Okay, follows just from this. So it suffices to show that what we subtract is at least as much as what we add. So let's try to do that. We'll have to somehow use the properties of these sets. And I mean, the intuition here is both of these are only talking about vertices where the value in the optimal x was not 1/2. It was strictly bigger, respectively strictly smaller than 1/2, which means you can take these variables and change their values a little bit and see what happens. Okay, so let's define some little epsilon, which is the smallest slack you have between any of the xv's in z0 and 1/2. So what's the minimal difference any of these has from 1/2? It's got to be non-zero, because these are just some real numbers, and we define z0 to be all the vertices that have a value strictly greater than 1/2. And so now we'll define some new vector, which is the same as x star, except for some entries. So when we have a vertex in Si, then we set this, let's call this x prime maybe. We set x prime for that vertex to be the old value plus an epsilon. And for the vertices in SC bar, we subtract the epsilon. And we know that this leaves the value at least 1/2 still, because epsilon was chosen so that for all of those there's more than that of slack. Yeah, epsilon is greater 0, but then the difference is greater or equal 1/2. Okay. And the claim is that this still fulfills the constraints. Which means we have to check that for every edge, this is true. Okay, maybe I'm running out of space here. Now, where could this be violated? It's an inequality, so it's only going to be a problem if I make variables smaller. So it'll only affect edges that have some endpoint in SC bar. Okay. And this was C0 without our S star. Let me continue on the next page for this. Now, if the other endpoint was in this set, IS, SI, no, it's not our SI. So in that case, W is not in S star. Because it's not removed, right? So sorry, I think this is V. I've changed names here. So let's say the vertex that we look at is V. That's the one. You could only violate this constraint for an edge where one endpoint is among those where we subtract something from XV. That must be in SC bar. And so we distinguish cases where this vertex could be. And suppose it was in this I0 without S star. But then we don't have this in S star. Why do we also not have the other endpoint in S star? I'm not sure anymore why this follows. Yeah, sorry, this must be the other endpoint. So we have one endpoint in SC bar. Then we distinguish cases for the other endpoint. It still follows now for both, because both vertices are in some set where we subtracted SC star. So if they were in SC star, they would not be in this set difference. All right, so that's true for V because of the assumption here. And it's true for W because of the case distinction. So if V is in SC bar, it cannot be in S star. That's why V is not in S star. If W was in this set I0 without S star, then it would also not be in S star. But then S star cannot be a vertex cover because there's an edge UV, VW that's not covered. So that case cannot actually be true. What other options do we have? We could have that W is in SI. In this case, it's one of those where we increment the variable by epsilon. Right, so x prime W is x star W plus epsilon. And so if you sum up the two, you satisfy the constraint. It's just the same as the old. They have a plus epsilon and a minus epsilon. And that was greater or equal 1 because it was an optimal solution. Okay. So then the third case is that W is not in I0. This was in I0, but not in S. This was in I0 and in S star. And now we have the case it's not in I0. That means its value is greater or equal 1/2, because it either was before or even further increased it, but it certainly it was not in this set I0. So previously it had a value of 1/2, and we don't subtract anything from it. And for our edge here, we subtract something, but we leave that above 1/2. That's this property. So if both are 1/2, then the sum is at least 1. Right? So in all possible cases, for the other endpoint of an edge where we might subtract something from its variable, the other endpoint makes up for it, or the case is not possible. And so we've proven that this new x prime indeed fulfills the constraints of the LP. Now, what do we get from that? Because x is an optimal solution of the LP, we get that the sum over all vertices in the new solution we construct cannot be smaller. And if you rewrite this, the definition of this xb prime, this entire sum here, we sum over all the vertices, and then it's the original xv, and then we have epsilon times something we subtract and something we add. So if we go back to the part here, what do we add? Well, we add epsilon for every vertex in Si. And we subtract something, we subtract epsilon for every vertex in SC bar. And epsilon was greater 0, right? So if you take this chain of inequalities together, it means that this difference must be at least 0. And so that means we've proven what we claimed here. It suffices to show that this SC bar is at most Si. That's the end of part 1. Okay? We've shown we can take an arbitrary optimal Z cover, we can transform it into one that satisfies the conditions from the theorem, namely include all the vertices where the variable is strictly greater than 1/2, and get rid of all the vertices that have values strictly less than 1/2, and the result is still an optimal vertex cover. Which means we can essentially assume that we fix this solution and just look at the remaining vertices, namely those with V0. So the second part of this theorem claims we have an induced subgraph where we only look at the vertices in V0, and we have to subtract from the threshold the vertices that we include for sure, namely those in C0. And then that is a valid kernel for the original input, and its size is bounded. Okay? So let's see that, and I need another page. So, for claim 2. First of all, we know the LP objective value, which, what was that again? It's the sum of the XV stars, right? Is never worse than the ILP objective value. That's what we used before. Now, the ILP objective value is the size of an optimal vertex cover. That's greater or equal than this thing. Sum of all vertices. And what we're going to do now is look at, so this is also true like for any graph, right? This is for any input to the vertex cover problem, this is true. So what we'll do is we'll repeatedly apply the following reduction rule. You take the LP relaxation of the vertex cover problem. That gives you some optimal solution X star. And from X star, you get these sets I0, I0, V0, C0. You remove or delete all vertices in I0. Include in solution all vertices from C0. And repeat this whole thing. So in each reduction step, we get rid of every vertex in I0 and C0. The only difference is that we keep track of the deleted vertices in Z0 because they will become part of the final output solution. And we're left with the V0 vertices. I think it's hard to prove whether one round of this reduction is enough, but we can just pretend we apply this reduction as long as we still get vertices where the optimal fractional value is not exactly 1/2. Okay? So after this, we'll have X star V is 1/2 for all vertices in our remaining graph. And let's call this V0 as before. Was defined like that anyways. At this point, what did I do? I think I zoomed. At this point, we'll invoke this inequality from above. And now we know exactly what this sum is. It's 1/2 the size of our vertex set, because every vertex has value 1/2. Okay? So what does that mean? It means the optimal vertex cover needs to pick at least half of the vertices in my graph. So there's two options now. If we have more vertices in the graph than our parameter allows, then we're doomed. We cannot possibly pick a vertex cover from those. There's not enough, our parameter restricts us too much. Okay, then we can, in terms of a kernelization, you output a no instance. And in the other case, means we don't have a lot of vertices. And so we get a bound on the number of vertices in the kernel. Okay. That's the end of this part. This shows how you can use an LP with a bit more sophisticated analysis to get a stronger reduction rule. One that doesn't simply use these local arguments we've done before, like just the degree of a vertex, but a more global picture, because the LP is really taking the entire graph into account. Let's do a tiny break. That section was a bit heavier. Okay, we might not make it through the entire section that's left. Before we continue, were there any questions for the vertex cover bit? I was trying to remember how we counted the size of kernels before, because we've just shown an upper bound of the number of vertices, not the size of the graph and the number of edges. But okay, I'll have to dig out what where the k squared that was just edges, or if there was a weaker argument also behind it. Okay, forget about it. We'll make a small pivot again away from algorithms and linear programs and back to, because the chapter is called Advanced Techniques for Fixed Parameter Tractability, a slightly more advanced technique for lower bounds again. In the last section on this fixed parameter tractable unit, we'll look at some further ways to show lower bounds for problems, so impossibility results. And what we've seen so far were W1 hardness reductions, where you could show a certain parameterized problem probably doesn't have any FPT algorithm. But what about problems where we do have some FPT algorithm, but we don't know whether we can further improve the functional dependence on K? So maybe let me spell this out. We had W1 hardness as the key tool. Probably not in FPT. And we had various techniques for designing fixed parameter tractable algorithms where that is not the case. How about problems in FPT? Can we somehow get lower bounds for this f of k? And of course, we'll pick on our favorite problem, vertex cover again. And remember, I had this on the slides previously. Vertex cover, we know algorithms with some constant 1.3 to the power k, k the parameter, the threshold of the size of the vertex cover, times some polynomial in n. That was possible. Can we do better? So whatever the constant was, I guess here we can safely put an n squared, and that's going to be enough. Can we improve this further? In particular, this part. And maybe at first sight, it seems, okay, what else could you do? Like if the function it's unlikely that we can show some polynomial. That would be amazing, but then the problem would be in P, and we would have shown P equals NP. So unlikely is very unlikely. What else could it be? It seems sometimes that there's nothing between polynomial and exponential, but that is very, very not true, very untrue. There's a lot of things between polynomial and exponential. And I mean, there's things like 2 to the square root n, which is not quite, is smaller than any constant to the n, but is also not polynomial. Or there's quasi-polynomial, where you have 2 to the log to some power of n. Say 2 to the log to the 5n, which is essentially the same as n to the log 4n. These are all running times that are, I guess I should have said k here instead of n, but as a function in n. These are all super polynomial, sub-exponential. And it's not clear if you can improve this to sub-exponential from what we've seen so far. All we have are upper bounds on this, and we have no lower bound for a vertex cover beyond probably not polynomial. Okay, and that's what we're looking at here. Now, to make statements about this, you have to make a slightly stronger assumption than our standard P not equals NP or W1 not equals FPT. And these are usually grounded on some complexity theoretic hypotheses, and one of those is the exponential time hypothesis. It's often abbreviated as ETH. It appeared in some slides before. And formally it says, if that is true, it's a hypothesis. Nobody knows, right? This is unclear, but many people believe in this one. It asserts that there is a constant epsilon, so that every algorithm for PSAT, where it's parameterized by the number of variables, I guess it says what k is. I wish I would have said p variables 3-SAT. So every algorithm for the 3-SAT problem requires some time 2 to the epsilon k. In other words, there is some 1 plus delta, and delta is greater 0. And we don't know what that constant is, but the hypothesis says there is one and it's not 0, so that any solution for the 3-SAT problem, in the worst case, asymptotically and so on, needs an exponential time. Okay? So again, nobody expects polynomial here, but there's a lot between polynomial and exponential. But the exponential time hypothesis says, no, there's, for SAT, it has to be exponential, at least. And we know at most as well. Okay? Now, the hypothesis itself is a bit unwieldy because it only says there is such a constant. It doesn't tell us what the constant is. So it's a bit hard to refute or make sense of. Depending where you look, you can reformulate it. That's what I already said. The same thing is to say there is some delta, so that 3-set algorithms need at least 1 plus delta to the k. Again, some exponential, just re-expressing how it's written. You could also say there's no way to have an algorithm with runtime 2 to the little o of k. So little o, again, was something that converges, some function that if you divide by k converges to 0. And that's not possible. And that is often the definition. So this 2 to the little o of k is usually what people describe when they say sub-exponential. Okay? That's why the name is called the exponential time hypothesis, because it assumes there's no sub-exponential algorithm for SAT. Alrighty. So far, that's just the definition. And the only thing I can tell you is that a lot of people believe that this hypothesis is sensible. And it seems any kind of algorithm for SAT has this property that it needs exponential time. So let's assume that this hypothesis is true. Or let's make this an assumption so that when we get some results, it would contradict this so that we assume the converse. That's how usual lower bounds work. So it's analogous to P and NP. We prove something is NP hard. What does that mean? Well, it means unless P and NP are the same, there's no polynomial time algorithm for that problem. And so we want to do the same thing with ETH instead of P equals NP, or P not equals NP. So we can use this to show that some problem X can be solved in some time that depends on some parameter of X. If that implies an algorithm that can solve the SAT problem in this time, so essentially contradicting what we've had for all possible epsilon, then that would refute the exponential time hypothesis. That's again the tricky bit. So this says there exists some constant, but it doesn't tell us what it is. So to refute that statement, we would have to show there is an algorithm for every possible epsilon that solves the SAT problem in this time. And in this case, so C, for example, could be a function of epsilon. It could be for any constant epsilon, n to the 1 over epsilon would still be a polynomial. But it has to decrease the base of the exponential part arbitrarily much. Okay. If we can do this, then unless ETH is false, we know that X doesn't allow such an algorithm. So we can try to kind of reduce problems to 3-set and get algorithms of that running time for a contradiction. The thing is here, this seems tricky because it needs a reduction where the number of variables in the resulting formula is small. And that's not always the case, or at least in many prominent examples, it doesn't seem to work. This is a reduction I've kind of very, very quickly shown you at the very beginning. We talked about classical reductions. It's also one that you'll have seen maybe in some other places or in Karp's paper. It's reducing 3-SAT to vertex cover. And it's just shown on an example. Here's some 3-SAT formula, and you can turn that into a graph where you take, for every clause, you make a triangle with the vertices containing the literals of the clause. And the triangle are these blue edges, and then the bit that encodes the logic are the green edges, which are connecting every pair of literals that are negations of each other. So here I have x1, here I have not x1, that's why there's this green edge. Okay? And then the reduction says that this formula is satisfiable if and only if there is a vertex cover for this graph that picks exactly 2 vertices from each triangle. And you can easily show that you have to pick at least 2 vertices in each triangle, otherwise the triangle edges aren't covered. And if you need more, then that means that some of the green edges were not coverable by just picking 2 edges. So in a way, the literal that is true is the vertex that remains uncovered by the vertex cover, is not part of the vertex cover. You don't need to dig through the details for making sense of what follows. The thing is that here, the parameter that we generate is 2n. We need a vertex cover that's linear in the size of the formula. And if the formula has n clauses initially, then it'll have 2n. It'll have n triangles. So you need to take 2n vertices in your vertex cover. So before we can make sense of that, can we say something about the number of variables here? The thing is, it doesn't seem to matter, even if the formula has very few variables, the reduction wouldn't give you anything different. The reduction would still look the same and ask for a vertex cover of the same size. So it seems tricky to make this faster by if you were the number of variables doesn't seem to influence the reduction, really. It's kind of ignored. Okay, maybe I can explain this bit and we'll do the rest of the proofs next week. So far, this is what the exponential time hypothesis theoretically gives us is not good enough to do reductions of the sort that we can get lower bounds for the f of k part in FPT algorithms. There's a key structural insight, and unfortunately, the proof of this is relatively lengthy and a bit more intricate. So it's only available in the original paper. It's not unreadable, but it takes us too far. So I'm just stating the result without the proof. But I want to explain a bit what it does. And in a way, it's rewriting a certain 3-sat formula so that the number of variables and the number of clauses are similar. Formally, it says for every parameter epsilon that you give me, there's some constant that I tell you, so that I can take your 3-sat formula phi with n clauses and k variables, and I can give you an equivalent formula, so it's logically the same, logically equivalent, which is a big disjunction of many smaller 3-sat formulas. And I'm using the same k variables in these formulas, but each of these formulas only has capital K times little k clauses. So the number of clauses is linear in the number of variables of the original formula. Okay? Now, this sounds like a magic thing. The problem is that the number of these formulas that you need is exponential. You can control how many you'll get and how long the whole thing takes by specifying this epsilon. So the smaller you make epsilon, the larger this k will be, but then the time and the number of formulas is slightly smaller. But you have to pick a constant greater 0, so it'll be exponential either way. You can just control how small you want it to be. So we do 2 to the epsilon k such formulas psi, and the overall computation, I guess, is essentially linear in the output. Okay. Because I put this here, let me explain what sunflowers means. It's basically if you have a collection of sets, so say these are literals of some 3-sat formula. and maybe there's a lot of clauses that include the same literals, but have some other literal added on them. Maybe a nonsensical one too. So the algorithm essentially tries to find these sunflowers, so sets of clauses that intersect all in some one or two literals. And then it says you can satisfy all of those clauses by either satisfying their center or by satisfying all the petals. So you can either satisfy this or all of those four together. And that's where this disjunction of three-sat formulas comes from. You get one part for the inner bit, either that is satisfied or the and of all the petals of what's left. And you need a clever recursive algorithm to make sure that you get rid of enough clauses that way. That's the part that's not very clean, or it gets very technical. Now let's, before we formally show this next time, let's briefly see why this is useful. The magic part here is that we take one three-sat formula and get potentially many three-sat formulas, but each of them is small in terms of the number of variables that we had before. And that ties nicely together to ETH. The exponential time hypothesis said nothing about the size of the formula, the number of clauses. It only considers the number of variables, but then it says it's exponentially the number of variables. With this sparsification lemma, we can take standard reductions like the one relating vertex cover and three-sat, even if they're only generating something in terms of the size of the formula, number of clauses, we can still use reductions against the exponential time hypothesis, because each of these psi's is sparse in this sense that the number of clauses and number of variables are the same up to constant factors. Okay, I'll show you formally how we make use of that then next time. That's all for today.